Good afternoon to our speakers from USA and good evening to all our attendees. My name is Pankaj Amin, President, ASHRAE Bahrain Chapter and MP Chair for the year 2021. On behalf of ASHRAE Bahrain Chapter and BOG, I welcome all ASHRAE members and other participants representing HVAC field covering design, engineering, sales, production, construction, facility, and engineering management. ASHRAE Bahrain will conduct many more technical webinars on our own webinar platform as well as jointly with the regional chapters. Special thanks and welcome to our technical presenter today from EMCA, Mr. Mikhail Ivanovich, EMCA Senior Director, Global Affairs, and Mr. Tim Matson, EMCA Principal Engineer, and Mr. Rob to deliver the technical presentation on new fan efficiency requirements in ANSI ASHRAE IES Standard 90.1 2019 in collaboration with ASHRAE Bahrain Chapter and jointly sponsored by Bahrain Trading Agency and Dynaya. Now I will invite Mr. Desi, our CTCC and Sustainability Chair and past President, to brief about ASHRAE and introduce the speakers today. Over to Desi.
Thank you, Mr. Pankaj, and good evening to you all, and thank you for joining in today's event. Today is the last second webinar in this series arranged by the Bahrain chapter, and inshallah we will arrange more of those. And to read out the mandatory code of ethics, in this and all the other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for all others, which exemplifies a core value of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and we shall avoid all real or perceived conflict of interest. As again, we have spoken about this last time also, research promotion is one of the important pillars of ASHRAE and which helps in supporting the research programs in at the society level. So those who like to contribute towards it, please let us know. We can arrange for the things to be done. And also just to remind you that membership is one of the important strengths of the chapter and the society. So again, we would like all of you to participate in the process and benefit out of it. Yeah, this again we saw last time that ASHRAE has arranged some of the courses which is online now. Few of the courses have already been conducted, but still there are few remaining ones, so you should be able to take advantage of this at a discounted prices. And for ASHRAE members there are certain discounts, but anyway the prices are quite low and it should be good for everybody. These are a few members who have joined our chapter since August. So since August, we have an addition of about 9 members. And in September itself, we have about 5 members joining in. So it's a good progress, but we need to keep it up so that the strength of our chapter increases further. Today's webinar is titled New Fan Efficiency Requirement in ANSI ASHRAE IES Standard 90.1 2019. The purpose of this presentation is to understand about AMCA International, the certification programs, and the fan energy index metrics that is going to replace the fan energy grade in energy codes and standards and regulations. To talk about this, we have distinguished experts on this panel now. Mr. Mike Ivanovich. Michael is a Senior Director at the Global Affairs of AMCA. He is the AMCA voting representative of SSPC 90.1 standard, energy standard for building except pro-rise residential building in the mechanical subcommittee. And he is also the AMCA representative for the state and federal regulation and legislations and utility rebate programs. He also coordinates the advocacy positions amongst AMCA's North American, Asia, Europe, and Middle East regions. Prior to joining AMCA, he was the president of his own research and marketing firm, the chief editor of engineering B2B publication, and a research scientist in the Pacific Northwest National Laboratory. Along with Mr. Michael, we have Mr. Tim Matheson. Mr. Tim is a principal engineer with AMCA since July 2019, where he works in the laboratory services and consults in codes and standards and advocacy efforts. Prior to joining AMCA, he was the principal engineer with GreenEck for over 31 years. Tim is an active member of several ASHRAE and AMCA technical committee, including ASHRAE TC 5.1 on fans. He was also the AMCA fan committee and AMCA engineering standard committee. He has represented many seminars or presented many seminars during the ASHRAE meetings and AMCA's technical seminars. He was later chair of the AMCA 208 committee that created the new FEI fan metric currently being used in ASHRAE 90.1. Tim also served on the National Technical Advisory Group to ISO TC 117, advancing American fan manufacturing interests internationally. I hope we will gain much insight into AMCA's activities today, and we will all gain experience out of it. Just before we start the seminar, there is the questions for the question answers will be done at the end of the seminar, but you can post your questions on the chat box, which will be compiled, and then we will try to and the panelists will try to answer that as much as possible, and those which are not answered can be replied by email also. Also, at the end of the webinar, there will be a webinar evaluation form, so we would like you to fill it so that we have your feedbacks on this. So now please join me in welcoming Mr. Michael and Mr. Tim, and let's have a very fruitful seminar. Over to you, Tim.
Okay, thank you, Mr. Desi. My name is Tim Matheson. I'll be your first presenter. I'm just waiting for the screen to be transferred to me. Welcome everyone to the webinar from AMCA International. Gentlemen, I'm not getting there we go. Now I've got an invitation to share my screen, and hopefully you can see that now.
Yes.
Okay, here we go. So again, welcome from AMCA International to this webinar where we're going to talk about a new fan efficiency requirement in ASHRAE 90.1 and some other codes. A reminder, this is copyrighted material, so use without the permission of AMCA International is prohibited. Our purposes and our objectives today to inform you about AMCA International, the Certified Ratings Program, the new Fan Energy Index metric, and how it's replacing FEG and some energy codes and standards. So at the end of this presentation, you should be able to explain FEI and how it's replacing FEG and some of these standards, how to apply FEI for sizing and selection of fans, and describe how FEI ratings can be obtained from fan manufacturers. So by way of outline here, I will cover the FEI basics. Again, my name is Tim, And Michael Ivanovich will cover the remaining 4 there, how FEI is used in ASHRAE 90.1 and 189.1, how to specify certified FEI ratings, and what FEI means in both constant volume and variable volume systems. And he'll give you some other resources on FEI. So starting with the basics, and first of all, why the change? So the 2016 version of ASHRAE 90.1 includes a requirement for a minimum FEG value for fans. And when the US Department of Energy started the process of regulating fan efficiency, this metric, FEG, was quickly removed from their consideration. Since FEG was not a wire-to-air metric, it didn't incentivize the use of direct drives or more efficient motors. And also, in order for a peak efficiency metric like FEG to actually save energy, a requirement was needed to apply fans within a certain percentage of their peak efficiency. While 90.1, ASHRAE 90.1 included such a requirement, the US Department of Energy can't technically dictate how a product is applied. And so the fan energy index was developed to address these shortcomings, and as such has now replaced the FEG requirement in the 2019 version of ASHRAE 90.1. So some of the issues that were addressed with this new metric, FEI is a wire-to-air metric, so credit is given for improvements to the efficiency of the fan or the transmission or the motor speed control. And instead of a peak total efficiency metric, FEI really reflects the power consumed at any potential operating point. And it's based on either static or total efficiency, as is appropriate to the fan type. Some of the benefits that you're going to see, hopefully you're going to see as I go through this presentation, the clarity of how this wired air metric allows instant identification of compliance, the flexibility in how FEI is used as a fan selection tool, comparing the various types and sizes and drive configurations for a given duty point. And because of this, you can quickly move on to other fan selection criteria like budget, cost, acoustics, etc. The simplicity of how this metric can be used to directly reflect power consumed by various fans. And all these benefits will result in greater energy savings, which is why AMCA developed this metric for eventual use in fan regulation, and why ASHRAE 90.1 has also adopted its use. Okay, fans can produce a wide range of airflow and pressure, but each individual combination of airflow and pressure is referred to as a duty point. So the output of a fan is airflow and pressure, and each of these points is a duty point. Now you could talk about specific duty points like the design duty point or as installed duty point, or you could talk about the peak efficiency duty point. But for now, just let's just use the term fan duty point to refer to a specific airflow and pressure within the fan's total operating range. So the output power of the fan is referred to as air power here, and it's simply the airflow times the fan pressure. And when we think about fan input power, usually we're thinking about fan input power to the shaft, but the FEI, again, is a wire-to-air metric. So instead of fan shaft power, we're concerned with the electrical input power to either the motor or, in this illustration, the fan speed control. Now, this picture is showing a belt-driven fan with variable speed drive, but it could just as well be direct driven, or it could be without a VFD. Regardless of the term or the configuration, The term FEP refers to the electrical input power to the fan system. Okay, fan energy index, as defined in AMCA 208, it is the ratio of a reference fan electrical input power to the actual fan electrical input power. So it's a wire to air metric. It's electrical input power. Both the top and bottom of this ratio are calculated at the same output power, the same fan duty point or airflow and pressure. So FEI becomes a relative measure of the power required for a given duty point. And so by relative, I mean relative to the reference fan electrical power. Now, people often ask, well, what is this reference fan, and who decided to make it a reference fan? Well, let me start by saying it's a reasonably efficient fan. And when you say reasonably efficient, obviously, who decided that? Well, it was established by the fan industry working with the U.S. Department of Energy, and the reference fan efficiency is fully documented in AMCA Standard 208. At the heart of this reference fan is an empirical function of fan efficiency versus airflow and pressure. Now this graph shows the concept. I'm showing here lines of constant efficiency. So the reference fan has to have this efficiency. So very large, high pressure fans are required to be very efficient. And then, as you can see in this graph, as the pressure is reduced, this reference fan efficiency is relaxed. And think about prop fans in that case. As airflow is reduced, and think about small fans, moving to the left on this curve, the reference fan efficiency is also reduced. The important concept is the reference fan efficiency only depends on airflow and pressure. We've kept it independent of fan type or fan size, motor type, motor size, whether it's belt or direct driven, only depends on airflow and pressure. And because of that, any combination of these variables, of any combination of fan type, size, belt, or direct drive, can be compared with respect to each other. Now, fan selection is an important part of FEI. As most people know, fan efficiency is very dependent on where the fan is operating on the fan curve. And most fans are selected to provide a specific airflow and pressure at a design duty point, airflow and pressure. Well, it turns out help is needed. And as we looked at, when we were developing this metric, we looked at typical fan selections. Here's actual fan selections for a single fan size. This is a square inline fan from one manufacturer over a period of a year. There are almost 300 fan selections. You can see on here the various speeds that the fan's available. You can see lines of constant efficiency drawn on here. This fan is not particularly efficient. It has a peak efficiency of 53%. But as you look at these blue dots, you can see that either fan efficiency is not a priority for people selecting these fans, or they simply didn't know what the efficiency was when they were making the fan selections. And we found this behavior to be very typical across most fan types. So when we look at FEI on a fan curve, a fan doesn't have a single value of FEI. It has a different value of FEI for each duty point within its range of operation. So this fan I'm showing just at a single speed. There's a pressure curve here. We can also plot an FEI curve versus airflow at a single speed. And the curve will always look something like this, rising up to some peak value near its peak efficiency, and then dropping off toward free air. When we establish some minimum required FEI for compliance, in this case I've shown it at 1.0, we can effectively define a range of compliant performance on the fan curve, shown here in the red portion of the pressure curve. Now, most fans are offered over a range of fan speeds. And if you are a seasoned engineer and you've got experience selecting fans from a paper catalog, you're going to appreciate the next few curves. But if you're a young engineer and haven't seen many of these, try to learn something from this and try to use this to help your understanding of FEI. So multi-speed fan curves like this are generated for the purpose of making fan selections. They can be fairly complex, but also useful. Start with a series of fan pressure curves at various fan speeds. So this fan is available from 400 up to 1600 RPM. Usually a surge line will be added with some advice not to make selections to the left of this curve. And then in the, so if we want to make a fan selection on this curve at design airflow and pressure, we can go into the curve and plot that point, and we can tell immediately that, yes, this duty point is within the fan's operating range. We can tell that it needs to run just under 1200 RPM, and we can tell that that design point is quite a ways away from the surge line, so we shouldn't be in trouble. We shouldn't get ourselves into trouble with surge. Now, oftentimes you'll see lines of constant power shown on the graph. So these can be either fan shaft power, as in this case, or they could be electrical input power if the fan is tested with an integral motor. So these are lines of constant power. Don't be confused so these don't correspond directly to the constant speed curves that are shown. These power curves could be at any speed, but all the duty points that are on those dashed lines, let's say the 30 kW line, all those duty points are at 30 kW. This is fan shaft input power. So from these curves, I can immediately tell from my duty point that the actual fan shaft power will be something less than 45 kW, and I'll probably need a 45 kW motor to power this fan. Okay, we can add more information to these curves. Occasionally you'll see lines of constant efficiency plotted on the curves. Now, so from these curves, I can tell that my design point is about 65% efficient, which is fairly close to the fan's peak efficiency of 70%. Now, fan efficiency is a real good measure for making fan selections. Intuitively, we know that higher efficiency means lower power consumption. There are a couple of reasons why this might not always be true, but generally it's true. But what might be a good efficiency for one type of fan or one fan application may not be a good efficiency for another type of fan or application. So here's where experience is needed to decide what constitutes a reasonable efficiency. Okay, so let's strip away all the other information and see how FEI is used to help make fan selections. So I've taken away the power and the efficiency curves, except showing that peak efficiency curve. Now, if I overlay lines of constant FEI on this map, they look something like this. These are concentric rings or bubbles that look somewhat like a topographical map. And once again, these are lines of constant FEI overlaid on the performance map. Notice that FEI is greatly influenced by the peak efficiency. You can see the highest FEIs are centered around that. As I said earlier, the reference fan will require a higher efficiency at high airflows and pressures. So as you move along that 70% efficient line toward the right and up to higher airflows and pressures, the FEI value decreases. But if we want to establish a minimum FEI requirement in a code, let's say minimum of 1.0, this establishes a range of performance for this fan that meets the requirement. So every duty point within the shaded area is compliant. And if the minimum compliant range was FEI 0.95, the compliant range for this fan is increased. You can see we can use it over a greater number of duty points. And now bear in mind, this is a fairly efficient fan. It's at 70% peak efficiency. A less efficient fan designed to do this same performance map will have smaller FEI bubbles. It will have a smaller compliant range. So you can see that FEI will improve fan selections. It allows comparison between different fan types, different fan sizes, different motor and drive combinations, all at the same duty point. So as I go back to this curve, my duty point was at an FEI of about 1.15. That meets the requirement set out here. Okay, so examples of how are you FEI in selecting some different fan types. So I've got two examples here, a utility set and a sidewall prop fan. So a utility set designed for 4.7 cubic meters per second at 500 pascals of static pressure, and a sidewall prop fan, which is a higher airflow, 9.4 cubic meters per second. It's at a lower pressure, 63 pascals. And you're going to see some pictures here of fan selection software, and they are in inch-pound units, so I apologize for that. So here's the utility set, 4.7 cubic meters per second at 500 pascals. For this design, for this design duty point, we can see there are 7 fan sizes that are able to do this requirement, from size 200 up through a size 402, and they're sorted in that way in this selection software. And we can look at the operating power right in the middle of the page, brake horsepower, and you can see it ranges by a factor of over 2. We've got some very low power fans at the bottom of the screen, and then it goes up to some very high values. So what I want you to notice is you'll see fan manufacturers with FEI printed in here, and this is very similar, nearly a factor of 2, reflecting the actual power consumed. Okay, so you can tell immediately from this selection screen, if our requirement was FEI of 1.0, the smallest 2 fans would not be suitable. And you can see also from the power that they consume, you can see why they wouldn't be suitable. Okay, let's go to a lower pressure fan, a sidewall prop fan, 9.4 cubic meters per second at 63 pascals, static pressure. So here we have more like 8 or 9 selections sizes that are available, somewhat from smallest to largest. And one thing to notice is the FEI column, or I'm sorry, the FEG column, and this is an explanation of why we're not using FEG anymore, is there's no indication from this, there's no relationship between FEG and the power required here in about the fourth column. It ranges from, again, a factor of more than 2, and all the FEG values are very similar. It's just that some of these are closer to their peak efficiency than others. But immediately with the FEI, we've got an index here that is directly related to the power consumed. So we've got this factor of about 2.5 from the worst to the best. Now, in this case, all of the fans available for this duty meet a FEI requirement if it was 1.0 or greater. The next example I want to show, if let's say those didn't all meet that requirement, and we said, well, what are the ways to meet the FEI requirement? Well, one of the ways, as has become obvious, I think, is to use a larger fan. Typically, a larger fan will reduce the power consumption. But in this illustration, I've actually made the selection at half of this airflow and said, well, what if none of my selections were okay, and I had to use, and I couldn't use a large fan. I couldn't use a fan that was 2 meters in diameter. How could I do that with a smaller fan? Well, I could cut the airflow in half, and while it says the same airflow up here, I've actually cut it in half for this selection. And now you can see the FEI for the smallest fan. If I go, I'm going to go back one screen. Our smallest fan here at 20,000 CFM was an FEI of 1.05. If that didn't meet our FEI requirement, I could cut the airflow in half for each fan, and with half the airflow through this fan, I've got an FEI of 1.7, much higher. And you can see that's reflected by the power. This fan, at half the airflow, this fan requires 1.07 horsepower. The previous fan at half the airflow required 3.5, so more than 1.5 times, or more, well over twice the power of the fan with the lower airflow. So that's a technique as well. But you can very quickly, from the FEI values here, show which fans consume the least power and which fans consume the most. I've got some examples of fans embedded in equipment as well, air handler supply fan and an air handler return fan. And so an air handler supply fan, you're typically not going to have any trouble in meeting FEI requirements 1.0, but oftentimes the return fan is at a lower pressure, and so you'll be lower on the fan curve, and sometimes it can be more difficult to match an FEI requirement. So I'm not going to, here are some screens that you might see, and I've made 3 selections for the supply fan, and then the return fan is at a lower pressure, 250 pascals, and looked at 3 selections for the return fan. And here's a summary of the previous slides. So I've skipped right to the summary. So for the supply fan, there were 3 sizes that were available, size 50, 56, and 63. And we show here the power, the electrical input power in kW for each of those fans was fairly similar, and the FEI value for each was well above 1. For the return fan, again, it's a little more difficult for a return fan because you're lower on a fan curve. You can see a greater range in power consumed and a greater range in the FEI. In this case, the size 50 did not meet the 1.0 minimum FEI requirement. So that is typical of what you will see in selecting fans in embedded equipment. Okay, so back to this screen that I showed before. This is just a summary. Hopefully you can see the benefits of this new metric FEI in its clarity, in its flexibility, and its simplicity, and hopefully that'll result in greater energy savings. We designed this metric for regulators, for regulation of fans, but the real winners, I think, with this metric are going to be the people, the design engineers who are selecting fans, who will get to know this metric FEI, and who will really like its versatility and like how they can specify energy savings with the use of this metric. Okay, so Michael will join us now to talk about how this FEI metric is being used in codes, standards, and regulations.
All right, thank you, Tim. Let me see if I can just grab the screen here. All right, someone gonna send me the screen? There we go, I think. Hold on one second. All right, Tim, can someone send me the screen? Let's see. Okay. I don't have, can you guys see my screen? There we go.
Not yet, I'm trying to do it.
I'm here.
There you go.
All right.
Yeah, no, it's fine.
So let me start my presentation. Thank you very much. I'd like to thank everybody for having Tim and I speak today. FEI can seem kind of complex. That's why we go into it with some detail. Tim did a fantastic job. He's a great teacher. I'm going to show you how FEI is represented in code, standards, and regulations. And it's actually from that perspective, from your perspective of being engineers having to comply with an energy standard, it's actually pretty simple in many cases. FEI is now in ASHRAE 90.1 2019, replacing the fan efficiency grade metric effective with that addition. I understand now that the SI edition of 90.1 is now available at the ASHRAE bookstore. That's great. It was published sometime in 2020. Also, FEI is in what we call a model energy code. There's something in the United States, primarily in the US, called the International Energy Conservation Code. And states generally adopt 90.1 or IECC. And so FEI is now in both, so we've got that cornered. We also have something called green codes or stretch codes or high performance building codes, and ASHRAE 189.1 and what's called the International Green Construction Code. Those two bodies have actually merged into a single document, and FEI has replaced FEG and what I'll just call ASHRAE 189.1, since this is an ASHRAE audience. So it's there as well. And I'll talk about the language that's in 90.1 and 189.1 affecting FEI. I think it's important just to mention that in terms of state energy codes, it's not really important to an international audience, except to say that these codes, model energy codes and standards are not really effective or active until somebody uses them or adopts them. And in the United States, the states of Florida and Oregon have now adopted the most recent editions of 90.1 or IECC. And so FEI will now start appearing in projects in the United States to meet energy codes. That's a big deal. FEI, as Tim may have explained, kind of originated from the U.S. Department of Energy starting a federal fan efficiency regulation. That started in 2011. but they never finished it. But at some point along the way, they said, we're not going to use FEG. We need something new. And so FEI was born. I'll talk more about that. But the federal efficiency regulation for fans is not finished. But one of our states, California, is developing something analogous to that, similar to that, but for only the state of California. It's a state efficiency requirement for fans, which is different than an energy code. It's a product efficiency requirement that applies at the point of manufacture, not a design requirement that would be in something like ASHRAE 90.1. And the significance of that is that California is expected to finish this year. The significance of that is once somebody establishes a regulation around using FEI, other states and other countries will jump in, because there's some complexities around FEI that make it difficult to express in a product regulation. It's actually more easier to use it in an energy code or energy standard, but for a product regulation, it's kind of tricky. And California, working with AMCA and our members, and we've got that figured out now. And once it's final, we expect other states to use FEI for product regulations, but also other countries. So that's why it's relevant to this audience. So continuing, we're going to focus really on what's in 90.1 and pretty much also in IECC, but this is an ASHRAE audience, so we're going to call it 90.1. In the language of 90.1 2019, it says that FEI has to be greater than or equal to 1.00, but if it's a VAV system, FEI can be as low as 0.95. And they do that to give credit for the fact that you might have a VFD on a fan that's running at full load. So the VFD has an energy, as an efficiency penalty, so to speak, at full load. And so we kind of gave credit. We didn't want that to hurt any fan selections. And so we brought it down to 0.95 for VAV systems. And it's important to note that FEI is calculated at fan system design conditions. And fan system design conditions are what the engineer, what you would specify as, this is the point at which you're going to select the fan. This is the duty point. This is the airflow, pressure, and density at which you want the fan to be selected. It might be, I'll talk more about it, but it might be at 100% flow for the hottest day of the year, or it might be a fan where you operate that fan 90% of the time. It's up to you to define what the fan system design condition is going to be for selecting your fan, and that's where the FEI is calculated at. And I say calculated, engineers don't calculate the FEI. As Tim showed, you have sizing selection software to use. The software will calculate the FEI. You just have to pick a compliant fan. So what's covered by this provision? Standalone fans, including powered roof ventilators, greater than or equal to 0.989, kilowatts, and embedded fans and fan arrays that are greater than 4.1 kilowatts. And it's worth mentioning the PRVs, powered roof ventilators, because with FEG, those types of fans didn't work with the metric. And so they had to be exempt from 90.1. FEI fixes that problem, and so now they're back being covered. The exemptions are worth paying attention to. I didn't list all of them, but there's quite a few, because we didn't want the energy standard to cover emergency fans, tunnel ventilation fans, fans for high temperatures, explosive atmospheres, etc. So those are exempt. Ceiling fans in the United States are covered by a DOE regulation, so they're exempt. We thought it was worth mentioning that in here. If a fan is not in the scope of AMCA standard 208, where FEI is defined, where the calculations for FEI are provided, if a fan is not in the scope of 208, then it's not covered by 90.1. A good example of that would be air curtains. Okay, so air curtains don't have FEI ratings because they can't be calculated using AMCA 208. But I'm going to spend a little bit of time talking about fans embedded in equipment that is regulated or third-party certified for energy performance. So if a packaged air conditioning unit or an air handler is AHRI certified, for example, or Eurovent certified for energy performance, then it's exempt from this requirement. Also, fans that are listed, there's a special section in ASHRAE, and that's not listed in this exemption list, but fans that are in what we call ASHRAE equipment, these are packaged equipment, heat rejection equipment, those types of things. There's another table for boilers. Those fans are exempt from the FEI requirement as well. So a lot of work was done to kind of limit the fan provision to primarily standalone fans and fans that are in air handlers greater than 4.1 kilowatts. So that's the guts of what's in the ASHRAE 90.1 requirement using FEI. As Tim mentioned, he showed you these bubbles. Just going to blow that up a little bit and show that anything that's in the shaded region up to 1.00 is the FEI requirement for constant speed fans. And you go a little bit outside it, and between 1.00 and 0.90 is the FEI greater than or equal to 0.95 requirement for VAV systems. So this is showing the compliant bubbles for 0.95 and 1.00. In terms of what's in ASHRAE 189.1 2020, its FEI has to be greater than or equal to 1.10. So it's slightly higher FEI requirement. There's no changes to what the exemptions are from baseline. In other words, whatever's in 90.1 that's exempt is also exempt from 189.1. So there's nothing new added. There's no removal of exemptions. And then also it's worth noting that the level does not change for constant or variable speed fans. So if you got a VAV system, it has to meet 1.10. If you have a constant speed system, it has to meet 1.10 if you adopt 189.1 for your design energy standard. Also worth mentioning, if this were the IECC, the International Energy Conservation Code, you'd have to have certified FEI ratings. Fans that have FEI ratings that are calculated by an independent third-party laboratory, such as the AMCA Certified Ratings Program. That is not required for ASHRAE. Personally, we do advise that you specify AMCA certified FEI ratings because internal to the software that you saw Tim demonstrate is that the FEI ratings have to take into account fans that are sold with motors and drives. And those drives could be belt drives, they could be electronic drives. The fans could be sold without a motor and drive, so we call those bare shaft fans. So there's all these options for how fans are sold. The motor could be regulated or unregulated by the U.S. Department of Energy. That factors into FEI calculation. So there's actually 7 different paths that manufacturers have to consider for their FEI ratings and encode all of those paths into their software. And so, the nut of it is that we actually recommend that you use AMCA certified FEI ratings because we go through the software to make sure that the software is accurate. And if you're going to specify AMCA certified FEI ratings, here's how you do it. You go to amca.org/certify, and you click on something called a certified product search, and then you click on search by license type, and then you click on FEI, and then you have access to all the FEI rated fans that are AMCA certified. So the vast majority of those certified products are going to be certified by certifying the software, not the specific fans. So the specific fans catalog might not show the FEI rating, but the software, which is pretty much what you want to use anyway, because you get all the options to choose from, that will be certified by AMCA, and that's the best way to find certified FEI ratings. And another thing to mention is that the way FEI was developed is that you can compare FEI ratings for different fan types. So you might be looking at an inline centrifugal versus a mixed flow fan. So FEI helps you choose between fan types, not just different fan models of the same type. And that's another reason to use the software. Okay. So this is kind of what the sticker looks like. You might see it on the product, or more likely you're going to see it on the fan selection software outputs. If it's FEI rated, you'll see the FEI rating, the certified sticker that AMCA provides that's in the software output. So I'm going to show you a little bit now about the behavior of FEI in constant speed and VAV systems, so you can see how you kind of check for compliance against the ASHRAE 90.1. So for this example, you've got an FEI requirement that has to be greater than or equal to 1 at fan system design conditions for other than VAV, and for VAV it's 0.95 as we've covered. The duty point that I selected for this example is that the airflow rate is 8.5 cubic meters per second. It's a static pressure rating of 1350 pascals, and the air density is at sea level. So there's your duty point. There's your fan system design condition right there, those 3 lines. And then for constant flow, the duty point that you're going to use to select the fan is at 100% flow. And for VAV, I created 3 hypothetical flows just to show you how FEI will behave at 3 different flow rates: 4.25 cubic meters per second, 5.95 cubic meters per second, and 8.5 cubic meters per second. So first, looking at constant flow, where the FEI has to be greater than or equal to 1.00. The hypothetical manufacturer software gives me 2 different fan types. As I mentioned earlier, you can compare against fan types, not just different sizes of the same model. And you've got fans that range in size of the airfoil double width from 464 millimeters up to 686. The FEIs at 100% flow for this fan type range from 0.90 up to 1.23. Drops a little bit at the largest size. You know, it's kind of physics. I don't really understand that, but it's not uncommon. Tim could probably explain it because he's an expert in fan engineering. And then the other fan type is backward incline, also a double width, and it's going to range in similar sizes from 464 up to 686 as well. And its FEI is going to range from 0.82 up to 1.17. So the first question that you ask is, which of these fans are compliant with ASHRAE 90.1? And the answer is, I shaded out the non-compliant fans in yellow, so anything below 1.00 is non-compliant. That leaves you free to select any of these fans for compliant fan selection. And I'll talk about a little bit more about what's the best fan given these options. Looking at VAV, similar situation. You've got 2 different fan types that are going to come out from the manufacturer's software: airfoil and backward incline, both double width. You've got 3 different flows: 40%, and 70%, and 100%. And the thing I wanted to call your attention to is that, first of all, the requirement is now 0.95, is that the behavior of FEI is at 100% flow. It's kind of give you your lowest FEI rating. That as you slow the fan down for lower flows, the FEI level is going to go up. But quickly, just eradicating the non-compliant fans. Okay, you've got the ones that are less than 0.95 are now covered up. You've got one case with the 16-inch backward incline. It's an overspeed condition. You don't want to select that fan at all. But notice now you've got, for the airfoil, you range from 1.05 up to 1.23 again. But notice how the FEI increases at the lower fan speeds. Now, you probably still want to use 100% flow for your fan system design condition, but you don't have to. But if you did, you'd be confident knowing that your fan would be running at higher FEIs at the lower flow rates. So what does this all translate into? It means that guidance for VAV systems, which is what we were asked a lot and why we developed these slides, was because slowing a fan's rotational speed generally increases its FEI rating, The best duty point for VAV might be the hottest day of the year, needing 100% airflow. So select a fan to have an acceptable FEI rating at 100% airflow, and this will ensure compliant at loads below 100% airflow. Now, careful reading of 90.1 means you don't have to be compliant at your lower flow rates. You know, the requirement is that you're compliant at fan system design conditions, but it's just kind of nice to know that when you select it for that design condition, the FEI will increase. Now, if you select the fan at 1.00 at its 90% flow, because that's where it's going to run all the time, and you have to run it up to 100% flow, your FEI level might decrease and be non-compliant at 100% flow, but that's okay. As long as you're compliant at the fan system design condition, you're compliant with 90.1. Other guidance is that if the fan meets the FEI requirement at peak condition, the fan will likely meet the FEI requirement at lower flow conditions. I'm being repetitive because repetition builds retention. And then you also need to know that you have to avoid surge and overspeed at all operating points. You don't deliberately choose a fan that's going to run in the surge region or at overspeed. So that's just general guidance for anyone picking fans. So giving those 4 or 5 options for the different fan types, you know, what's the best fan? And basically that's up to you. Once you're compliant with the energy requirement, you're free to consider the other things that go into selecting a fan. Form factor, you know, the shape of the fan and size, its weight, what's your budget, what's the energy cost, so that you might go up to those higher efficiency fans. They'll cost more, they might be bigger, but your energy penalty, you know, is far reduced, greatly reduced. You're running a lot less energy, so your energy cost savings will be much higher, and it could pay for those extra size or that extra weight fairly quickly. Generally, it does. You know, the energy costs for the larger fans, the cost savings generally pay for themselves and within several years. And then the acoustics, also very, very important, and of course availability. If you can't get the fan you want when you need it, you know, you have to pick a different fan. So just letting you know that once you're compliant, as engineers, you're free to use your engineering to select the best fan. So that ends the content part of the webinar. Just want to point out a few resources that are available to you. In particular, the very bottom one, amca.org/FEI, that's a one-page microsite, so to speak, for all things FEI. You could link, you know, there's the link to the bookstore for getting the FEI standard, AMCA 208, if you wanted to see what goes in, you know, what's under the hood for FEI. Calculations you don't have to make, but you might want to see them to believe them. There's regulatory updates, there's PowerPoint presentations, white papers, all kinds of technical resources for understanding this new metric. And then, as I mentioned, you can look for FEI certified ratings, AMCA certified FEI ratings at amca.org/certify. But these are all good resources for you to continue investigating and using FEI. And with that, we're ready for questions. So I'm going to mute myself and go back to our moderators. Thank you very much, everybody.
Okay, this is Tim. I'm not hearing Mr. Yunus.
Mr. Yunus, you are muted. Yunus, can you unmute?
You have to unmute.
Okay, I still can't hear him, but I can see a couple of questions on the screen. So I'll start with the first question. This is from Mr. Singh. So how will FEI selections result in energy savings versus FEG selection of fan? And so I did briefly talk about FEG on one of the slides. If I could summarize those, FEG is a very good metric for determining how efficient a fan is. how good of a fan design is reflected in the FEG. FEI, on the other hand, is a very good metric for determining how good is the fan for a particular application. So for a design duty point, airflow and pressure, FEI is a metric that really tells you how good the fan is for that application. So you may see an example would be a airfoil centrifugal fan has a very high FEG level. But if you were to try to use an airfoil centrifugal fan to do a very low pressure application like a sidewall prop should be doing, you will consume more energy with that airfoil centrifugal than you would with a sidewall prop fan that a sidewall prop fan that may have an FEG of 50 or so, a very low FEG. So FEI is more related to the how a fan is suitable for an application. I can go to the next one. Why FEI?
The next question is from Mr. Ashok Patel, and he's asking why FEI of 0.95 is allowed for VRV system compared to FEI of 1 for the fix.
Yeah, okay, that's a good question. So as Michael said, there is going to be some loss for the variable speed drive, and so that is part of it. The other part of it, I would say, is the lower FEI allows you to select the fans lower on the fan curves. If you remember the shape of those bubbles, the lower FEI requirement will allow you to go further down on the fan curve. And what that really helps is in turn down. With a variable volume system, all your energy savings comes from reduced speeds. And so we don't want to, by requiring a high FEI value, we don't want to reduce the allowable turn down on the fan.
Okay. Next question is from Mr. NP Singh, and he's having two questions. First is, will there be any difference in construction of fans with FEI selection, or it is just for the purpose of clarity of efficiency or power consumption? And the second question is, why FEI rating is acceptable as 0.95 and without VFT not less than 1?
Okay, so I think I covered the second part of that in the last question. So back to this one. So will there be any difference in construction of fans with FEI? With FEG, you might see fan designers trying to design fans with a higher peak efficiency because that's what that metric is based on. Whereas with FEI, you may see a shift to fans that are more appropriate for a given duty. So when designing fans, we can give up a little bit of peak efficiency to be able to cover a broader range of operations. So we might, as a common term today, flattening the curve. Instead of a very steep efficiency curve with a high peak, we can design the fan in a different way to make a broader efficiency curve that's a little bit lower in peak, but it's extended out to a further range.
Yeah. Can I add some commentary to that, Tim?
Yeah.
Okay. So when we were developing the Department of Energy regulation, they informed the fan industry that they could not use FEG because it was not wire to air. It did not include the effects of motors and drives. It's only good for bare shaft fans, and that it was peak total efficiency only. So we couldn't apply it to operating points other than peak efficiency. And the sizing selection window, the fans have to be sized and selected to operate within 10 or 15 percentage points of the peak total efficiency. FEG only works with that sizing selection window. And a couple things, it's difficult to enforce, people forget it, but from a federal regulation perspective, they can't even use it. That window is applied at design, not at the point of manufacture, and regulations take effect at the point of manufacture. So FEG failed on 3 different ways to be useful for a federal regulation. So when FEI was developed, it built in that sizing selection window because one of the things that AMCA was able to show is that fans operate most often not at their peak load, that they run much more often at part loads. And so if you're going to save energy, you really want to have a metric that applies at the part loads. So that's one of the reasons where FEI is very, very strong. Anyway, the other thing about the FEI was that I don't know where I'm going. I lost my train of thought, so I'm just gonna go back and hopefully say that I covered it, Tim. I just lost my train of thought. That happens. Okay, so back to the next question.
Next question is from Mr. Ala. He's asking, is the FEA rating will force the fans manufacturer to change their current fan design to get higher rating of FEA?
Well, it's possible that that designs could change. I think the thing to keep in mind is those FEI bubbles. How large are they? If a particular fan design has a very small compliant window, a fan manufacturer may choose not to sell that at all. They may take it out of their portfolio. Whereas they may design fans with larger FEI compliant bubbles by making them more efficient. And by designing them more efficient may mean either the impeller, or it could mean shifting to more direct driven fans, so avoiding the belt drive inefficiency, or offering those fans with higher efficient motors as well. So those are some changes you might see to current fan designs.
Okay. We have 2 more questions that from our panelists. They will ask you directly. Faranji, you can ask.
My question was regarding the one slide which Tim showed, that instead of 20,000 CFM, we can select 2 fans of 10,000 CFM to meet FEI. So the question is that will meet the FEI criteria, but what about the other costs that will incur, like cabling, panels, etc.? How that will be mitigated?
Right. Okay. So yeah, I slid over that pretty quickly and didn't do a lot of explaining with that. The FEI will not consider the other things like cabling, like you mentioned. I was just introducing that as another possible solution to compliance. And it's very unlikely that if I need one fan today to do a certain duty, that I'm gonna even consider doubling that, right? Where you might consider that trend though is if you've got a warehouse or a distribution center with 20 axial fans ventilating up on the rooftop, and you say, well, I'm having a hard time meeting that FEI with those 20 fans, so instead of 20 fans, maybe I'll use 24 fans, and they might be one size larger. than what I'm currently using. And in this way, you know, the FEI will reflect the energy consumed. We've got that covered. But as you mentioned, there are going to be other costs involved with that. So it is, I just pointed out because most of the selection screens, it's pretty obvious that to save energy, you need a larger fan, right? But you don't always need twice the size fan, or, you know, it may be just a little bit larger and it may work just fine. So hopefully that answers.
Thank you.
Mm-hmm.
I think it's worth mentioning too, Tim, that they could switch over. They could get a different drive or a more efficient motor as well. And FEI does take that variety into consideration.
Right. That's right.
Thanks.
Next question is from Mr. Atul. Can you ask?
Yeah, thank you for this presentation. My question is regarding the constant flow fans. When we have a fixed duty parameter, then is there any relationship between the total fan efficiency and FEI?
I'm sorry. This is Tim. Could you repeat that one more time? I got the end of it.
Yeah. I'm just asking about this relationship between the fan efficiency, total fan efficiency, and FEI for a constant flow duty parameters.
It will be the FEI will be greatest most typically at the peak efficiency point of the fan curve. That's typical.
Yeah.
There may be some exceptions to that where it's slightly off.
I think the only thing to be cautious of is that, especially heading into, but in the United States, it's going to be a regulatory environment. Certain fans will have to be rated at static pressure, and certain fans will have to be rated at total pressure. And Tim can correct me if I'm wrong, but generally the breakdown is that if it's a ducted fan, it's going to be rated at total pressure, and if it's an unducted fan, it's going to be rated at static pressure. Is that about right, Tim? Or
that's right. Yeah. No, that's right.
So you have to be very careful in your fan selection process is to know whether or not you're heading into a total pressure selection or a static pressure selection. And when you look at manufacturers' ratings, you know, the test configuration will determine if it's an unducted or an unducted fan. And so if it's, you should be careful that if you have a total pressure application, you're selecting a fan that's been rated at total pressure. Because I've seen some selections where they miss that detail and it causes problems. Because some fans are actually rated in both total and static, just because the manufacturer wanted to do that. But in a regulated environment, United States, you'll be forced to do your compliance rating at static or total. You can still rate it at the other pressure configuration if you want to for marketing purposes, but it's just a general guidance. Is be very careful that your rating, your manufacturer's rating approach, you know, configuration matches your application.
Thank you.
We have more questions, but due to the time constraints, we are not able to take it right now, but we will get back to you through your mail.
Yes.
And over to Mr. Farhan, the President-elect, Master Bahrain chapter, to give the vote of thanks.
Okay. Well, it's been a pleasure. Can't thank you enough for the invitation. It's been fun. I hope you found it interesting. And Tim, any last words from you?
I will just mention there was one question that got my interest. The asker said, I need to share this information with the company to update our specs accordingly. We talked about meeting regulations, but you should also think of this as a way to meet customer expectations. If you have a customer who you know has a priority on efficiency, you may specify a higher FEI than 1.0. You may specify 1.2, and then let the bids come in as they will, and just be able to hold that spec. So that's all. It just reminded me of that.
Thank you. Good evening, ladies and gentlemen. It gives me immense pleasure to deliver the vote of thanks for this wonderful evening. It was a terrific lecture by our eminent guest on the topic New Fan Efficiency Requirements in ANSI ASHRAE IES 90.1 2019. I'm sure every one of us has gained valuable knowledge. So a big thank for our guest speakers, Mr. Tim Matheson and Mr. Michael Ivanovich. And also, I would thank Mr. Rob, who supported back of the house areas. And I'm really thankful to him as well. This wonderful event became possible due to vigorous efforts of our digital team, consisting of Mr. Vinod and Mr. Yunus. I can say with conviction that everyone enjoyed it. So a deserving thanks for both of them. Finance is backbone of all events, and we are fortunate to have our sponsors who always stood by us. I take this opportunity to thank our sponsors, BTA, Dyneer, and AMCA International, whose valuable contribution made this event possible and successful. We have a series of events lined up for this year, and we wish to see you all again. The next event is in third week of this month, a lecture organized by BTA and Train. And also on 26th of this month, a lecture with one of the prominent speakers of the region at large, of which we shall be sharing the details of registration very soon. Last but not the least, thanks to all of you for joining in great numbers and making this event so successful and unique. Please do not forget to give your valuable feedback so that we can improve on our upcoming events. One more good news I want to share is that our webinar shall be available on YouTube very shortly. With this, we conclude the webinar. On behalf of ASHRAE Bahrain Chapter President, Mr. Pankaj Amin, and ASHRAE Bahrain Chapter team, we thank you all. Stay safe and stay healthy. Good evening and good night.
Thank you, Mr. Tim. Thank you, Mr. Rob. Thank you, Mr. Michael.
Bye-bye.
Bye.
Bye. Bye.
Thank you.